Welcome to the Cumulus Parameterization talk. Here we'll deal with the Cumulus Parameterization part of the physics, which is a name-list option CU physics. Cumulus Parameterization interacts with some of the other physics. It produces clouds for the microphysics. It produces convective rain, which goes to the surface and interacts with the land surface model. It also provides a cloud fraction for the radiation in some cases. A cumulus scheme activates in columns, and when it activates, it provides a heat and moisture or cloud and possibly momentum tendency profiles in the column over the cloud depth. At the surface, it provides a convective part of the rainfall. This is a similar diagram as the one I showed for PBL schemes, but now the main energy containing modes are the deep convective updrafts that are in the 1 to 3 kilometer size scale. At coarse grid sizes of 10 kilometers or more, you're not resolving these updrafts, and therefore you need a cumulus parameterization scheme that handles updrafts and downdrafts as subgrid scale fluxes, deep fluxes from the boundary layer to the upper troposphere. So that's what this talk is mostly about, is how to do this parameterization. And it's all done in a 1D column model. When you're at finer grid sizes of 1 to a few kilometers or less, the dynamics is resolving the updrafts explicitly. So between the dynamics and microphysics, they handle resolving the whole convective system. And you don't need to do any parameterization except for the microphysics and rely on the dynamics. These are the processes we have to deal with in a convective parameterization. All this is in one grid cell. Basically, you have the updraft mass flux and the downdraft mass flux. Downdraft will also be driven by rain evaporation. The updraft is driven by buoyancy of the boundary layer air relative to the mid-troposphere. There's detrainment, which will include a lot of vapor and cloud. And then there's compensating subsidence, which occurs in the same grid cell. The dynamics responds to the heating, but the updraft and downdraft and subsidence do not produce a net vertical mass flux themselves. They only produce the heating, and the dynamics will respond to that. So cumulus schemes have to be used for grid columns that completely contain convective clouds, typically 10 kilometers or more, because of the assumptions in the schemes that compensating substance is also occurring within the same grid cell. So they redistribute the air in the column to account for vertical convective fluxes. The updrafts take boundary layer air upwards, the downdrafts take mid-level air downwards, driven by rain evaporation. The schemes have to determine when to trigger a convective column and how fast to make the convection act and remove the instability. Schemes work in individual columns that are considered convectively unstable. The mass flux schemes, which are what most of the WRF ones are, transport surface air to the top of the cloud and include environmental subsidence around the clouds. Note that, like I said before, the schemes have no net mass flux, so subsidence compensates the cloud mass fluxes exactly. Environmental subsidence around the cloud warms and dries the troposphere, removing the instability over time. The dynamics may produce mean vertical motion in the grid cell in response to the scheme's heating profile. Additionally, the downdrafts may cool the boundary layer because they are driven by rain evaporation and transport this cooler air to the boundary layer. This illustrates how a mass flux scheme works. It has to represent the updraft mass flux, taking boundary layer air and into the upper troposphere and detraining it at cloud top. This may be a small fraction of the grid cell. Also, there's a subsidence term which compensates for it so that there's no net mass flux in the column. So the mass flux in the updraft may change with height according to entrainment and detrainment. And so you get a dmu dz, which is a function of height. Mu is a function of height. The compensating subsidence balances this mass flux, so there's an equal mass coming down as up, which has a corresponding substance velocity which is slow compared to the updraft one because it's a larger fraction of the area. Updraft transport conserves moist static energy because there's condensation occurring, so temperature and moisture will not be separately conserved, but the moist static energy will. So some schemes are written in terms of a conservative quantity like moist static energy. Others are written in terms of temperature and moisture with a condensation term. But as the updraft is ascending, the moist static energy will change with dilution due to entrainment, but so the model can predict the updraft moist static energy as a function of height. And also it uses this to predict the cloud top level, where the level of neutral buoyancy is achieved, and the cloud will then detrain. Substance occurs around the updraft and is just a vertical mass flux term. It's a ddz of the theta or q term flux. So substance leads to warming and drying in the environment just due to descending motion. This diagram illustrates the downdraft in addition to the updraft. So in summary, the updraft is driven by buoyancy, takes moist air to the upper troposphere, and condensation in the updraft leads to convective rainfall. Downdrafts are driven by convective rain evaporation, and they bring evaporatively cooled air to the boundary layer. Substance warms and dries the troposphere, and it's the main warming effect in the column is the subsidence. So WRF has two main classes of cumulus scheme, although the first class is only represented by one of the schemes. This is the adjustment type, Betz-Miller-Janich, which relaxes towards a post-convective mixed sounding. So it's taking the post-convective sounding, which is sort of like a moist adiabat that conserves all the quantities compared to the initial state, but it's relaxing towards that sounding. The mass flux scheme explicitly treats the updraft and downdraft mass fluxes. So this is what I just described, where you take an updraft mass flux and that's transporting air physically from the boundary layer to the upper troposphere, and reverse happens for the downdraft. So the cumulus schemes in WRF, there are many choices. Kain-Fritsch is a traditional one, has been in the model for the longest. Betz-Miller-Janich also, mainly developed at NSAP. Grell-Freitas and various versions of the Grell scheme are available. Grell-Freitas is just the latest of the various Grell schemes. It's becoming quite popular now as well. Tiedtke is one that we use. It comes from the European Centre model. It's one that we use quite a lot, especially at global scales. But as you see, there are a lot of choices here. When you run a cumulus scheme, you have to decide when it activates, and this is called the trigger. You need the presence of some convective available potential energy in the sounding, but not too much inhibition or capping in the sounding. And also, for deep convection, there's a minimum cloud depth that's considered to be deep convection. Also, the schemes need a cloud model, as I mentioned, for the updraft. These are basically a 1D cloud model that calculates the vertical variation of updraft properties based on the initial properties at the base, entrainment dilution from the environment, condensation producing cloud particles, a conversion of cloud to rain that falls out of the updraft, and buoyancy, which determines the cloud top and the detrainment level. So all these are handled in a one-dimensional simple cloud model with basic condensation and growth into rainfall inside that cloud model. Closures are the term given to how to determine the strength of the cloud. So in the case of mass flux schemes, the mass flux itself has to be computed somehow. We don't know that in advance, so we have to have a way of producing that. Various methods include how a timescale over which it removes CAPE, or quasi-equilibrium assumption, where the rate of production of CAPE by the environment is balanced by the rate of loss of CAPE due to the cloud stabilization. Moisture convergence is another kind of closure, and the low-level ascent or mass convergence is another kind of closure. But the most common closures are the CAPE removal timescales. So there you have to then come up with what timescale you want to remove the convective instability over. Another thing to consider is scale awareness, which is introduced by reducing the deep convection mass flux based on criteria such as grid size. When you're starting to resolve the convection explicitly, you'd like the convective scheme to be less active. So one way they do that is by reducing its mass flux to make it less active. The Grell schemes are basically an ensemble of methods. They don't use a single trigger and closure, but they actually use a combination of several and average them. And so it's several triggers, several closures, and maybe a few varying parameters within them. Could be up to 144 members that they average together. And then that average gets fed back to the model as an ensemble mean cumulus behavior. In principle, you can tune their members to optimize them under various conditions, but what's currently produced or released is the ensemble average. So far I've talked about deep convection, but actually we also have to deal with shallow convection in some way. Shallow clouds are distinct in that they're non-precipitating usually. The mixing dries the PBL and moistens and cools above the boundary layer. This can be done by an enhanced mixing approach or a mass flux approach. So the enhanced mixing approach is just increasing the diffusion coefficient, or the mass flux approach is kind of like the deep convection scheme where it actually does a transport. So we have both those types in WRF. Shallow convection could be useful at grid sizes that even resolve deep convection. So grid sizes down to 1 kilometer, you may still need a shallow convection scheme, even though you may not need a deep convection scheme. So WRF has several different ways of treating shallow convection. One is with the deep convection schemes, as listed at the top. KF and SAS in the Grell schemes, they do have a shallow component with them. But also we have some standalone shallow schemes listed here, including some that we've extracted from the deep scheme, NSAS and KSAS, that can be run alone using this SHCU physics switch. There's also the Deng shallow scheme, which is part of the WRF solar physics development. Grimm's shallow scheme is developed with the YSU PBL scheme. The other way of running the shallow scheme is as part of the PBL scheme with mass flux methods, and often when they add the EDMF approach, they also include the shallow clouds with that. So we have these listed here, including the MYNN EDMF option within that scheme. Some cumulus schemes also handle a momentum transport, taking momentum from the boundary layer to the upper troposphere. Most schemes transport it as a passive scalar, but there are a couple, the Zhang-McFarlane and the NSAS, that include a convective pressure gradient term that modifies the momentum as it's transported. Most schemes detrain cloud and ice at the cloud top as well as the vapor. The exception is BMJ that only detrains vapor. Kain-Fritsch also detrains snow and rain. That's the only scheme that does that. These detrained species are then used by the microphysics. Cumulus schemes also have a radiation interaction. The Grell schemes, Kain-Fritsch and MSKF, interact using the CURAD feedback equals 1 switch, which allows them to provide a cloud fraction and an amount for the radiation in active grid columns. So in other words, the radiation does see the convective clouds in these cases. Zhang-McFarlane is part of the CESM suite, and in combination with the MG, Morrison-Gettleman microphysics, they produce cloud fractions, and the UW shallow scheme, they produce cloud fractions for the radiation in their own way. The GFDL radiation, which is an option I haven't really talked about much, it's an old option, but it does have a way of interacting with clouds by only needing information on the precipitation rate in the top and base of the clouds. So it can interact with any of the schemes that provides that information. There's also a switch called cudt in minutes, which is a time between cumulus schemes calls, and it may save some computation time because it then doesn't look for clouds except for at this frequency. And when you search for clouds, that takes some computer time. So also for Kain-Fritsch, this time is used, it's the averaging time for the vertical velocity trigger, so we recommend 5 minutes for that and not changing it. There are some schemes like the Grell schemes that don't actually use this switch, and we'll try to look for new clouds at every time step. This is another summary of the cumulus schemes we have, summarizing their moisture tendencies that they provide, the momentum tendencies, whether or not they provide them. Sometimes that depends on the dynamical core that's being used. The shallow convection, similarly. Some of them include a shallow convection and some don't. And then radiation interaction and how they interact with GFDL or even directly with RTMG. So in terms of choosing whether to use a cumulus scheme or not, here are some recommendations. Greater than 10 kilometers, you probably do need a cumulus scheme. These release the instability gradually and prevent grid point storms. The resolve scale will not do very well at producing strong convection at these kind of grid sizes. It delays it and it then becomes too strong. So definitely you need a cumulus scheme if you have a convective situation at greater than 10 kilometers. Less than 3 kilometers, you probably don't need a scheme. However, there are cases where the earlier triggering of convection by cumulus schemes helps. 3 kilometers is also marginal for tropical convective clouds where the updrafts tend to be thinner, but it seems to work reasonably well, even especially for hurricanes, where you probably don't need a cumulus scheme because they're strongly forced. Part of whether you need a cumulus scheme or not depends on the forcing. Fronts and things will force convection to occur at the right time and with a reasonably good magnitude. Whereas if it's weakly forced and the clouds are left to develop in an unstable environment, the timing could go wrong if you're not using a cumulus scheme in the right resolution. In the 3 to 10 kilometer range, it's called the gray zone, where there's a scale separation issue that the updrafts are not fully within a grid cell, including the substance area. There are a few schemes specially designed with this range of scales in mind. There's a growing number now, but the Grell schemes have an option to, G3 has an option to spread the substance into neighboring columns. The GF and MSKF and KSAS do phase out deep convection at finer grid sizes. And GF actually turns it into just the shallow part of the scheme at fine grid sizes. Also, if you're running convection on an outer domain and no convection on an inner domain, like with the 9 and 3 nesting, for example, you might see discontinuity in the rainfall pattern across the boundary. Solutions to that are either to run the cumulus scheme on the nest or to not run the cumulus scheme on the outer domain, or to do one-way nesting to avoid the interaction between the domains, because actually the convection on the outer domain can suppress some of the convection in the inner domain when it triggers earlier. So there are these interactions to look out for when you change physics across the resolutions. But you are allowed to turn on or off the convective scheme depending on which nest you're running. So finally we can summarize the cumulus schemes. The cumulus schemes, as I mentioned, have to be run At coarse resolutions, they're not designed to run in fine resolutions. They represent the deep convective clouds and provide the convective part of the rainfall for the surface, also interacting with the radiation and microphysics in the ways I've mentioned.